All right, today we are taking a really close look at the engineering behind LangGraph. It's a framework that's been built from scratch specifically for making AI agents that are actually ready for production. And if you've ever tried to take one of those cool agent demos and turn it into a system that people can rely on, well, the struggle is real. So let's break down exactly how LangGraph is designed to solve that problem. I really love this quote. It kind of hits the nail on the head, right? The biggest competition for any new tool isn't another tool, it's just not using one. It's just writing the code yourself. So, for a framework to even be worth your time, it has to be so much better, so much more helpful that it's a no brainer to use it instead of just winging it. That begs the question, doesn't it? There are a million frameworks out there. Why on earth do we need another one just for AI agents? Well, the simple answer is that agents aren't just another program. They are, well, a completely different beast. Okay, so let's talk about the production problem because to really get why LangGraph exists, you have to understand the problem it's solving. It's all about moving from that cool demo to a system that actually works, and that's a huge leap. Deploying an agent is nothing like deploying a standard web app. You run into a whole new class of problems that your usual engineering playbook just doesn't cover. And this is really the heart of the matter. The magic of large language models, their creativity, their flexibility, that's the very same thing that makes them such a nightmare in production. We are not just calling a function that adds two numbers and gives you back a predictable answer in a millisecond. We are dealing with something fundamentally new and unpredictable. So, what makes these agents so difficult in production? It really comes down to three core challenges. Everything we're about to talk about, every design choice in LangGraph is a direct response to one of these three things. So let's dig in. First on the list is latency. And we are not talking about a few extra milliseconds with agents. We're talking about runtimes measured in seconds, sometimes even minutes. Think about it. An agent might have to call an LM multiple times, fetch some data from an API, call the LLM again. All of that adds up. And from a user's perspective, a blank screen for 30 seconds feels like an eternity. They're just going to assume it's broken and bounce. Number two, reliability. It's simple math, right? The longer something runs, the more chances it has to break. Now, with a simple rep request, you just retry it, no big deal. But imagine your agent is 9 minutes into a 10-minute job. It's analyzed a bunch of documents called three different APIs and then it fails. Starting all over again from the beginning is just not an option. It's incredibly frustrating and it's also incredibly expensive in terms of API calls and compute time. And the last one, this is the big one, it's the magic ingredient that also causes the biggest headaches, non-determinism. The user can type anything and the LLM can say anything back. There's no way to predict or test every single possible interaction. How do you build a reliable system on top of something that's fundamentally unpredictable? How do you even debug it when something weird happens? It's a huge, huge challenge for building safe and predictable products. All right, so we've got our three big problems: latency, reliability, and non determinism. So, what do we do about them? This is where we shift from just talking about problems to defining a concrete list of must have features. What do developers actually need to build agents that can survive in the wild? So, here are the six things you absolutely need to deal with latency. You need two things: parallelization, so you can do multiple things at once instead of one after another, and streaming, so the user sees progress and doesn't think the app is frozen. It's all about managing perceived latency. For reliability, you need a task to manage retries in a smart way, and this is a big one: checkpointing. Remember that agent that failed after 9 minutes? Checkpointing lets you save your progress along the way so you can just restart from the last successful step. It's a lifesaver. And finally, to tame that non determinism, you need a human in the loop, a way for a person to step in, check the work, and give the green light. And you absolutely need good tracing so you can look under the hood and figure out why the agent did what it did, especially when it does something unexpected. Okay, a fair question. If we know what we need, can't we just grab an existing tool off the shelf? Well, people tried, and it turns out the old tools just don't quite fit. Take something like Airflow. It's built on what's called a DAG, or a directed acyclic graph. The key word there is acyclic, meaning no loops, but agents need loops. They need to be able to try something, see if it works, and if not, loop back and try something else. So that's a non starter. When you have tools like Temporal, which are designed for long running tasks, very closer. But they weren't built for this new world. They often lack good streaming support, can add their own latency between steps, and this is the real killer. Their performance tends to get worse and worse the longer the task's history gets. For a complex agent, that's a total deal breaker. And that's exactly why LangGraph was created. It's a new design built from the ground up to give developers the control and durability they need for building agents. It wasn't adapted from an old paradigm. It was designed specifically for this new one. So, what's the big idea inside the LangGraph engine? It's all about this concept of structured agents. Instead of writing your agent as one giant messy function with a big while loop, LangGraph makes you break down the logic into small, manageable steps. You can think of them as nodes in a graph. Now, that might sound like extra work at first, but this structure is the secret sauce. It's what makes everything else, checkpointing, human in the loop, parallelization, even possible. So, how does this thing actually run? It's pretty cool actually. It uses an algorithm inspired by Google's Pragel system for processing massive graphs. Here's the loop. First, it looks at the current state and figures out which steps or nodes are ready to run. Second, and this is key, it runs all of those ready nodes at the same time in parallel. Each one gets its own little sandbox to work in. Third, once they are done, it takes all the results and merges them back into the main state. And it does this in a predictable deterministic order, which is super important because it means no race conditions. Finally, it repeats the whole process until there's nothing left to do. This whole cycle makes the agent's behavior repeatable, which is a dream come true for debugging. Okay, that all sounds great in theory, but how does it actually perform? How does it scale? Because that's the real test, right? A framework that's fast for a simple demo but falls apart under a real workload isn't very useful. So let's take a look at the performance characteristics because this is where the design really pays off. Before we dive into the next slide, just a super quick refresher on something called BCO notation. Don't worry, it's pretty simple. It's just a way to describe how an algorithm's speed changes as you give it more and more data. All you really need to know is that O, which is constant time, is the holy grail. It means it's just as fast whether it's handling 10 items or 10 million. On the other hand, ON or linear time means it gets slower as the input gets bigger. Alright, here's the performance breakdown. There's a lot of information here showing how performance is affected by things like how many nodes or channels you have in your graph. But I want you to ignore all of that for a second and just look at one specific row, the one that says length of history. See that across the entire row, for every single action, it's O1, constant time. And that is the crucial point. This is the whole ball game right here. What this means is that LangGraph's performance does not slow down, no matter how long the conversation is or how many steps the agent has taken. This is a massive departure from other systems that get bogged down by history. You can have an agent that runs for an hour with hundreds of steps, and the next step will be just as fast as the first one. Why? Because the engine only has to look at the very last checkpoint to decide what to do next. It's a total game changer for building complex agents. Okay, so let's zoom out for a second and think about the future of agents. What does all of this mean? The whole philosophy behind LangGraph is about choosing low level control over high level magic. In a field that is moving at lightning speed, the thinking is that it's better to give developers powerful fundamental building blocks rather than trying to guess what the right high level abstraction for an agent is. It's a bet on flexibility and control. So let's just recap the key takeaways here. Building agents for production is uniquely hard because of latency, reliability, and non determinism. LangGraph gives you a toolkit of 6 specific features to tackle those problems head on. The whole thing is built on a design that prioritizes developer control and durability. That structured design is what enables its amazing performance, letting it scale beautifully without getting bogged down by history. And all of this leaves us with a really interesting question to think about. LangGraph makes a clear trade off. It chooses explicit control over simple convenience. So, as these AI agents get more and more powerful and more autonomous, is this kind of low level, high control framework going to be the only way we can build systems that are truly reliable and safe? It's something to chew on as we all build the future of this field. Thanks for tuning in.